Alright, Brandon Clayton here, the Algebra Guy. Today, as you see on your screen, we will be discussing exponential functions and pretty much everything concerning exponential functions. What exactly do you ask? Well, I'll put it up here on the screen so we can all see it. Let me bring up my little tool. Alright, so we're going to be looking at domain and range from an exponential function. What does the a and b mean in the actual function? Because the function is f of x equals a times b to the x power. But what do a and b mean? And what does x mean? So we're going to talk about those as well. Also, we're going to talk about writing exponential functions in this form, a b to the x, where b is a rational number, describing problems arising from growth and decay. So there's two types of problems you'll see with exponential growth problems and decay problems. And lastly, we're going to talk about some key features like wire-intercept, asymptote, domain and range, as we mentioned a second ago. So let's jump into it because we got a lot to cover, as you can see. All right, so the first question I want to ask you is, what if you had what option would you pick? If you were given the choice of working 30 days, you could receive a penny a day, that's doubled every day for 30 days, or you can get $200,000 after 30 days. Which one would you pick? The answer seems easy, right? Now, most students, as I know you probably were thinking about, is going in for that 200 grand, right? Like, when's the last time you got 200 grand and got that opportunity? I'm just taking that right away. However, you knew there was probably a catch to this because it seems too good to be true, and you're right. If I doubled a penny every day, what would that look like? That look like a penny. Double it again, that's 2 pennies. Double it again, that's 4 pennies. And 8 pennies and 16 pennies. And you're like, this is not going anywhere. Give me the 200 grand. However, if we looked a little bit deeper, look what you're going to discover. It does move in that direction, 2, 4, 8, 16. But let me show you the power of exponential functions. This thing is growing exponentially. And it's literally, in this case, doubling each time. So 10 to 20, 20 to 40, 80. Now you're going from a penny to $163 in only 2 weeks. Now look at what happens when you get down to day 25. At day 25, let's go to day 26. You're already at $335,000. You've already have exceeded if you would have chosen the $200,000. So you're missing out on $130,000. And you're thinking, whatever, I got my 200 grand. But when you go further, oh my, to day 30, you're at $5 million. Let me say it, $5 million. Now you're sick. You're like, that 200 grand is nice. And you're probably okay because you're like, I got a lot of money in my hands, but this ain't gonna last as long as 5 million. And you would have thought, only if I knew how to do the math, I could have calculated this and figured that out. And if it would have been a 31 day, what if it was a 31 day month? You at how much would that be? 10 million. And I'm hoping that's what you said. So let's do the math. So that's what we're here. So let's go ahead and do the math. Let's break down this function first. What form does an exponential equation have? What does each part represent? So here's the function for an exponential equation. We just saw what that looked like. That's if you have a rate that stays the same each turn or each year or each set amount of time, the rate doesn't change and it keeps increasing by that rate, 50% every year or 100% every year or 8% every year, whatever it is, that's exponential. Also, it can decrease at that rate. But let's break down this form here. So if we were taking this form, let's talk about what a, b, and x represent. So a is going to represent, as you see right here, our original or initial amount. This is what we start with. What would that have been in our penny case? Well, in our penny case, what did we start with? We started with the penny. We said, what if you have just 1 penny? So that would have been our a right there. Now, what would have been our b? So what would have been our b? So I said each time we're doubling. So which number do we use for doubling? So this one I would use a 2 because we're doubling. And I'm going to put a parentheses around this 2 because I'm going to take this to the x power. And x is going to represent our time. So we're going to say this is to the x power. Let me use a different color. We're going to say that's to the x power so much time. What does the y equal? Y is the final amount, right? That's how much money we had at the end. So if we were looking at the problem we just talked about, here's what the equation will look like. And we could have calculated to figure out how much money we would be making at the end of so many years. So I'll put it over here as well. A is our original. that initial amount that we start with. B is going to represent our rate of change, which would have been 2 in this case. And if B is greater than 1, in this case it is, that means we're going to have a growth exponential equation, a growing exponential equation. And we have a B, we're going to have a decay. That means it's going to be decreasing just as fast as we saw it growing, which can be absolutely scary, right? If it's the wrong thing. Now, if it's your debt, that's great. If you owe somebody, that's great. Anything that's bad, you want to go on away exponentially. But also we have time here for our X. So we're going to look at those and apply those here in the next slides. Here's our first slide. Let's talk about these different aspects. Now, we talked about domain, range, and before, but I want to introduce a different term, which is asymptote. And these are peculiar or particular to exponential equations. So what do I mean? So let's get into this equation first of all. It says Maria's bank balance can be represented by f of x equals 5 times 0.5x. She was told that her money should grow over the coming years. Is this true? And if so, by what percent? She was told her money should be growing. So look at the equation. Here's our equation here. And should her money be growing? Let me see. I think I could pull up a graph that goes with this one. And yes, there we go. So here's the graph that goes with it. So we can see clearly from looking at the graph that this is actually decaying. Now, I didn't actually need the graph, because if I would have looked at my equation here, I would have realized that there's an A here. Here's my B, and here's the X. Well, the B is between 0 and 1. It's a fraction. It's a decimal, right? So I know that this is going to be decaying, going down, which as you see here, the line's going down from left to right. So I'm going to circle decay. Now, let's reinforce what we talked about before with y-intercept, domain, and range. Now, y-intercept is going to be where it crosses the y-axis. It's going to be right here at this point. But what is that point? Well, it's easy because we know that's our initial where we started at 5. So our y-intercept is at 0, 5. And if you weren't sure, you could have put 0 in for x. And anything to the 0 power is 1. So 1 times that first number is just going to be 5. Now, what's our equation? We're already given our equation up here. So we can just copy that down here. Domain is all my x values. So it can go from all the way. So I'm drawing that line kind of funky to show you that it's going to go all the way up, yes, but it's going to keep going to the left is what I really want you to see, to the left side. Don't think that line's going to go straight up or you're going to miss that. It's going to go keep infinitely going to that left side. So it's going to go all the way to the left and then keep going all the way to the right. No, it's not going to stop here at -2 or -3. So since it goes all the way to the left and all the way to the right, we're including all the real numbers. How do you represent that? All real numbers. So x such that x is all real numbers. So this is how it's read on your test, and oftentimes you'll see it that way. So what about the range? Now the range goes all the way up for infinity, as you can see with this arrow, but it doesn't go down for infinity. Matter of fact, it goes all the way down to what looks like 0, but it's not. It gets very, very close to 0, but it's not 0. Why? Because it continues to take half of something. Well, let's just think about it. If I have 1 and I take, well, let's say 2, and I take half of 2, I got 1. You take half of 1, you got a half. Half of a half, you got 0.25. Half of 0.25, you got 0.125. Half of 0.125. As long as you have something there, you can continue to take half literally forever. So we're going to say that this line is never going to touch the 0. It's never going to touch this x-axis or y equals 0. Now it gets really close. Let me see if I can draw a line that illustrates this for you. I actually want it to be a dotted line, so I'm going to kind of sketch this out. If I drew a dotted line across here, this line represents a line that is never actually going to touch. It's never going to touch, but it's going to get really, really close to. Matter of fact, the big word that is often used here is it gets arbitrarily close, but it's never going to touch. So I'm going to say it can be anything. The range can be anything that's greater than 0. But it can't be equal to 0. Why? Because it never touches 0. So all my y values greater than 0 can be equal. Now, why did I go into the explanation about this dotted line? Because that is our asymptote. Our asymptote is the equation of that line. There it is. That's the equation of that line of the that it gets arbitrarily close to but never touches. And this line is most of the time going to be y equals 0. Now sometimes you're going to see that line shifted up or down, but just know that whatever invisible line is getting really close to, that's your asymptote. Yeah, it's a funny sounding word, but that's what it is. So we got the A was our 5, the B's are 0.5, and we are good to go. Let's see, we got everything, we got the equation already up there. All right, next problem. Let's see if you can do this by yourself. The value of an antique coin is tripling its value every year. In its first year, it was only valued at 40 cents in 1942. Write an equation that could be used to determine the value of the coin in X number of years. So what equation could I write to represent this? I will pause it here and see if you can come up with the equation that we could use. Now, I'm hoping you tried it already, but what equation could we use? Well, let's think about this. What's our initial? So let's get our A and B. What's our initial? What are we starting with? So first year is at 40 cents. So I'm gonna start with 0.4 because that's my initial. That's what we're starting with. And my rate, how fast is it increasing or decreasing? It's tripling. So I want to actually put a 3 here because it's tripling. Is it going up or down? The value is tripling its value. So it's going up, right? Because this number is greater than 1. So I'm going to say this is growing. Now, where is it crossing the y-axis for the y-intercept? Well, I'm just going to graph this on my calculator, and if I did, it'll look something like that. Now, I could have figured this out. Why? Because it starts at 40. At year 0, when x is 0, it starts at 40 cents. So I know that there's going to be a 0.4. So that's what we see right here. It looks like half, but we know for sure it's 0.4. What's the equation then? Well, we have all our pieces right here. So now we know it's y equals ab to the x. So a is 0.4. Some people like to write 0.4, which is fine. And they got 3 to the x power. And there it is. There's our equation. And this equation allows us to find the value at any year. So if I plugged in 2, I could find out what the value should be at 2 years, 3 years, and so on, 2.5 years, if this rate continues. All right, so what about domain and range? Well, domain is going to be the same as before. It's going to be everything because it's going to all the way from the left side, all these negative values, and it's going to keep on going forever to this direction. Even though it looks like it's going to go straight up, it's not. It's going to slowly keep going this direction. So all real numbers. And our range again is the lowest it can go is 0 and everything above. So everything that's greater than 0. Can it be equal to 0? I'm really hoping you're saying no. Why? Because it gets really close to the line but never actually touches. And at that line we call it an asymptote. And again, this one is at y equals 0. And it's tempting to say x equals 0 because y equals 0 represents the x-axis. But remember that all the points on this dotted line have a y value of 0. This point is 3, 0, 4, 0, 5, 0, 6, 0. You get the point. You get it? No pun intended. You get the point. All right, so anyhow, all the y values have a 0. So that's why we're going to say the asymptote's at y equals 0, because there's a line right there that represents what it's getting close to. All right, let's go to our next one. And we have in this one, the population of a town is tripling every year. In the year 2018, their population was only 2 people. Write an equation that could be used to determine the town's population in X number of years. So first of all, what we're starting with? We're starting with only 2 people, but they're tripling. That means they're growing. My y-intercept is where they started at 2 people, so I know that's at a 0, 2. Now, if I were to graph that, it'll look the same. So let's graph it. Bam, right there. You see it's going right through the 2. So that wasn't tough to figure out. My equation is easy now because I recognize the main parts. My initial is 2. My rate is 3. And my x is so many years, right? So whatever I want to put there to figure it out. My domain is still going to be x is all real numbers because this thing just keeps going forever to the left and to the right. All the negative numbers and all the positive numbers to the right. On the x-axis, left and right. Now for the range, again, it's going to be everything greater than 0, not equal to 0, because look, And this is important because on tests, they draw the line like this and it makes it look like it's getting really close, but it's not going to touch. It looks like it's going to touch, and you better believe they're going to have an answer choice there that says y is greater than or equal to 0, because they want to see if you understand that this is exponential. And though, yes, that line looks like it's right on top of the x-axis, trust me, it's not. It gets extremely close and they can't show you that. So please say that your asymptote is y equals 0 and your range is greater than 0 but not equal to it. Everything above that 0 but not equal to. All right, you try this one, please. If you can get this one, I know you're getting it. Pause it here and you work it. No, really, pause it. Work it. All right, so hopefully you worked it by now because you're a person of integrity and you're doing that, so thank you. And we're going to start with our initial, right? So what's our A and B? 1.5 grams of an ingredient found deep beneath the Earth's surface decomposes. You know what that word means? That means it's breaking down at a rate of 70% each year. Write an equation that could be used to determine the amount of this ingredient that's left. How much is left? We want to know how much is left after X number of years. All right, so this is interesting here. We started with 1.5. What's our rate? No. I bet many of you are saying 70%. This is a tricky one because we actually want to know not how much is decreasing by, we want to know how much is left. So if 70% is being lost, how much is being left over? Well, what's the rest of the percent? Well, percent means per 100. So it's actually going down at a rate of 30. I mean, we're actually leaving 30% each time. Why? Because we're taking away 70%. That's going away and we're leaving only 30% behind. Now let me say that one more time in a different way. If there was a 70% off sale, it was $100 shoes and it was 70% off. That means they're taking away 70%, $70. And if we wanted to know how much is left that I need to pay, we're going to save 30. And in that case, it's $30. So please keep that in mind when writing the equation, because this can trip up many students as well. This is a decay problem. We know that by the word decompose. And the y-intercept is where we started at 1.5, 0, 1.5. And we can also see it right here on the graph if you were to graph that. Of course, you need the equation to graph it. So that's what we're going to put together now. Y equals 1.5 is where we started. And this time we're going to write 0.30 to the x power, because that's telling us how much we're keeping, how much is left each time, not how much we're losing. Now, if they wanted a graph of how much is being lost, that's what you would put 70% for. But they said they want to know how much is being left. So our domain, again, is still going to be x is all the real numbers because it keeps going from to the left. All these numbers over here and all these numbers over here. So left and right, it goes on forever. The range, again, is everything that's greater than that 0. And the asymptote is equal to 0. And let's try some star problems that we would normally see on a star test. So if you were to take in a test, here's the kind of problems that showed up. In 2017, here's one of the problems. And actually, do I want to get my, no, I don't think I'm gonna need my calculator for this. So let's just look through it and see. So a student uses f of x 5 times 1.012 to show that the balance in the savings account will increase over time. What does a 5 mean? Oh, this is so fun. Look, you should, if you remembered the basic format of this and what each piece means, this should be a piece of cake for you, right? You remember this A? A starts for A as in the beginning of the alphabet. A is starting, initial, where we begin. Well, guess what? Here's our A right here. Here's our B, and here's our X. X is time, B is our rate. So that's easy. What does the 5 represent? That represents where we started. So the interest, the savings account earned for the first year. So that looks tempting. You see it's first in there. The annual rate, the annual interest rate of the savings account. No, that's not the rate. It's not the rate. That's the B. The number of years the savings account has earned in interest. No, we don't want to know the number of years. The number of years is going to be our X. The starting balance. The starting balance. This sounds better. Now, why isn't it the first one, which a lot of students would have been tripped up by if they remember something dealing with the first? Trust me, they put that in there for a reason. The reason it's not this one because the interest of the savings account is only going to come after you do this operation. After you finish this whole thing, you can figure out the interest when you multiply this little 12% by the dollar amount. So you need to know that this 5 is starting out with how much money they started out with, because that's what we're counting up. We're not counting his interest. His interest is included in there. So the starting balance, where he started out with, is what we want for that question. Let's try another one. All right, back in 2018, here's the one that was given. Scientists are studying bacteria. We got this function, 245 times 1.12 to the x power gives the number of bacteria after so many days. Which statement is best in the interpretation of one of the values of this function? What's the best interpretation of what's going on here? Before we look at anything, let's interpret it ourselves. 245 means what? That means what we started with. What are we talking about in context? Well, we're talking about bacteria. So that must mean we started with what? 245 bacterium. I think that's the plural for bacteria. Didn't know I knew that, did you? So 1.12 is what? That's telling us that this is the rate. So I'm going to say this is starting with, and let me put down here, this is our rate. Now, is this rate going up or down? Depends. Is it greater than 1 or between 0 and 1? Well, this is obviously greater than 1. It's 1.12. So this is a rate that's growing or increasing. And then this X just stands for our time. So many days. X stands for so many days. So now let's see which one makes sense from what we just talked about. The initial number of bacteria is 12. Nope. We just discussed that. Now, I want to share with you what I just did. I don't look at the answer choices first. Why? Because I don't need the answer choices for help for the problem. You know this. You got this. Sometimes by reading the answer choices first, you can fall into a trap because they've set it up for you to say, oh, that has the word first in it, or that. No. We know what we know, and I already made notes to it. So now let's answer the question. The initial number of bacteria decreases at a rate of 88%. No, we just said right here. It increases. You got 1.12. Number of bacteria increases at a rate of 12%. That sounds good. That has a 12 in it. The number of bacteria at the end of one day is 245. No, it's actually at the beginning. Before they start anything, it's at 245. This 12% is the right answer. Why? Because we have 1. That represents just the starting number. 245 times 1 is 245. Then we added on this decimal part that says 0.12. So that's the percentage that it's increasing by. It's increasing by 12% each time. All right, which one of these statements is true? Look at this graph here. Is it the range is a set of, now we're talking about domain and range again. Is it the range is a set of all real numbers less than 0? The range is all less than 0? Really? How can that be? There is nothing down here. This line doesn't even go down there. Oh, that's ridiculous. And I hope you can say that too when you're taking a test, because you're so good at this. You're like, please, you can't trick me. So now we only got 3 other answers to go through. The domain is a set of all real numbers greater than -4. So here's -4 right here. It's saying it can only be all the numbers from here to this side. This line is never going to cross. This line is never going to cross there. Well, we know better than that because we just practiced that this line will cross. It'll continue going that direction slowly, but it's eventually going to cross there forever. So no, it's not going to be limited. It's going to be all real numbers. The range is a set of all real numbers greater than 0. That sounds more like what we talked about. So let me erase all this. Let me get my eraser bigger. So, because we talked about how the range will go as low as 0, but it won't actually touch 0. So all this and above. So this one sounds pretty good. The domain is a set of all real numbers less than -4. All the real numbers less than? You mean it can't be anything on this side? Absolutely not. All these numbers, these x values, this -2, -1, 1, 2, 3, these are all points on this line. So this is definitely not right. It's not numbers less than -4. If nothing else, I could cross out those 3 and know that C was the right answer, but we would have known that anyway. So good job to you. What about this one? The amount of fertilizer in a landscaping company warehouse decreases at a rate of 3%. So it's decreasing. Sometimes it's good to highlight these key features. The amount of fertilizer in the warehouse originally, hey, there's that word, we started out with 78,000. Which function best models this? So I'm not even going to look at the function. I know I'm going to say y equals, we're starting out with 78,000. And I know they want to know which model, how much is left. Okay, watch that. Not how much it was decreasing by, but how much is left. Well, after you take 3% off, what percent is left? Well, 97% is left. So this is going to tell us how much is left. Actually, I'm not going to write 90%, 7% there. We're going to write the decimal portion of it. So that's 0.97 to the x. And you can better believe they're going to have a 3 in there, but I know that's not right. We start with 78,000. I know that for sure. So let's cross out anything that doesn't have that. Nope, nope. Now we're at 50%. And look, this test so often you can cross out at least 2 of them because it's that simple. And you can close your eyes and have 50-50 chance, but we're not going to do that. We're actually going to do the right way. So here's a case students will struggle with. Is it 103 or 97? So I know it's one of these, but here's what we remember. If they're taking away the 3%, we have left 97%. So this is the one we're interested in. So that's the one I'm going to pick. And good for you for not falling for the trap. I hope you didn't. And this was a very commonly missed problem. So let me read through this last problem. I believe it's our last one. A toy is made up of a cylindrical ring stacked on a base, as shown in the diagram. The diagram of ring 1 is 87% of the diameter of the base. For ring 2 through ring 7, the diameter of each ring is 87% of the diameter of the ring directly below it. So this looks complicated as all get out. But the first thing you need to know is this. The percentage, the rate is the same each time. So as we go, which way? As we go up, it's getting smaller. So we have a decreasing exponential function here. So what do we start with? So let's look at our base. A toy is made up. The ring 1 is 80% of the diameter. Ring 2. So what are we starting out with? The diameter of the base is 5. Okay, there it is. We're starting out with 5. So I know we're starting with 5. So guess what I'm going to do? I know that for sure. I know that in my form, a b to the x, we're starting with 5. Now I'm going to reiterate that this is exponential because on the test, it's not going to say that. It's not going to say, hey, this is exponential. You're going to be wondering, is this a linear equation, quadratic? Is this math stuff? No, look, they said 87% for the first one. It went down 87% for 2, for 3, 4, for every single time it's going down at the same rate, at the same percentage rate. Don't confuse that with a line that moves at the same slope. They have the same slope up 3 over 4. Notice that we're dealing with percentages now. So 0.87% and so on. So these are the same rates that it's moving. So we know it's going to be a starting out with 5. Let me say y equals. We know we're starting with 5. We know, what do we want? The diameter of the base. Which function can be used to find the diameter? The diameter is decreasing. So what's this 80%? The diameter of 80% of. So we're taking 87% of the diameter before it. So which one do we want? The remaining piece of 87% or the 87%? Well, it looks like we want, well, let's save that. Let's do what we know. And we know this is going to be raised to some time, right? To some limit. We're not talking about time in this case, we're talking about the radius. So we know we need 5 in front. So let's see which ones we can know it's not true. It can't be that one and it can't be that one. And we know it's going to be 2 some power. So we can look at and decide just from that is going to be F. So we got our 87% on the inside and to the R power. Now this can be, it's not raised to that power, and it's just going to be more of a linear movement, but this is not going to give us an exponential decreasing. So F is going to be our choice. Now I wanted to show you this, that through the process of elimination, just knowing that this is my initial, knowing that this is exponential can help me solve problems like this. All right, let's go to our next one, which is it. So did we do it all? Yes, we conquered it all. Domain and range. We talked about A and B in this meaning, growth and decay, and the key features including y-intercept and asymptote. Guys, thanks for tuning in. Again, my name is Brandon Clayton, and I will see you next lesson.